been doing with Danny Turno at Macquarie Uni, and Danny thought the quantum gravity talk is more interesting, so he's not here. This idea revolves around, so the idea of Discord really revolves around the question, what is a quantum system, or when is a system a quantum system? And I think the standard or most basic answer would be, if it's entangled, it's quantum. So what I'm going to try and convince you is that most states are quantum. In fact, almost all of them are quantum. Almost all separable states are quantum. And quantum discord captures this quantumness. So just a very, very quick overview of what people have been doing. So quantum discord was introduced. Okay, it's a measure of quantum correlations. I should probably mention that. And it was, so you've got total correlations in a system, and you want to find the quantum part of these correlations. It was introduced in 2001. And in about the last 5 years, people have been using it to study a lot of different systems and what's quantum about those systems. So thermodynamics, quantum computing, quantum information. I'm mainly going to talk about thermodynamics and quantum computing. We're currently doing a review. So just so you get the order of magnitude, about almost 200 papers in the last 5 years on Discord. So people really happy about studying Discord. Of course, the fact that people are studying it doesn't mean it's interesting, but that's the situation. Okay, so the way I'm going to be selling Discord is going to be a bit strange, because the first thing I'm going to say is when we've got some quantum operation that's LOCC, so that's the main paradigm I'll use. You've got Alice and Bob, they're in two different labs. One is here in Canada, the other one is in Australia. And they're trying to do some operation. They're allowed to have, they're allowed to communicate, and they're allowed to do local operations. And they only have one quantum resource, entanglement. Okay, so that's really important. The resource for doing the operation is entanglement. But what I'll show you is that when they're trying to think, is this a quantum system? Do I need quantum resources in order to manipulate it? Looking at entanglement is not enough. And you should be looking at something like Discord. And there's one good intuition into why not all states, well, almost all states are quantum correlated. And you can think of maximally entangled state that is with noise. So you add noise to a maximally entangled state, you mix it with a completely mixed state, and you start, so think of the Bloch sphere, and you start going down the Bloch sphere, and as you hit a certain point, which in this case is 1/3, you stop being entangled, which is a bit strange. I mean, why is this boundary, why does this boundary tell us that we stop being quantum? If you think about entanglement as a measure of quantumness, that seems a bit strange. And Discord really measures it right down to the center. So you're getting a whole lot of new states that are quantum inside this ball. Okay, so the outline of my talk is, I'll talk about distributed quantum gates. That's kind of my personal motivation for looking at Discord. So this will be an example of where we've got a system that has no entanglement, but still needs entanglement resources in order to do a very, very simple operation. And we'll see that most states that go into this operation, a controlled NOT gate, need quantum resources in order to be manipulated. Then I'll explain what is quantum discord. And then I'll show two examples of using quantum discord. So one is Maxwell's Demon, and the other one is going back to my example of distributed gates, and why is it interesting there. Okay, so this is how I started looking at Discord, and I think this is the big breakthrough that made all these papers come out in the last 5 years. So not this paper. So we all know that for pure state quantum computation, we need a lot of entanglement in order to get an exponential advantage. But even when people showed that they can simulate states that don't have a lot of entanglement. So if you've got a computation and at some point you don't have, well, at no point you have lots of entanglement, then you can simulate the computation. And the proof basically relies on the fact that entangled states are correlated. So it really breaks down when you go to mixed states, because you can have mixed states that are not entangled and are still correlated. And the speculation was maybe mixed states can help you more. A little bit before that, people discovered this DQC1 algorithm, which is an algorithm that can do something exponentially faster than any classical algorithm for the same problem, and it has very, very little discord. So very quickly, what is DQC1? It's a protocol, well, one use for DQC1 is finding the trace of a unitary matrix that has an input of 2 to the power of n qubits. Of n qubits. So if I've got n qubits, I've got 2 to the power of n diagonal elements. Summing them up will take 2 to the power of n operations, give or take. So it's a hard problem. DQC1 solves it, and not only does it solve it solves it with a single pure state. So you've got instead of the unitary, you've got a controlled version of the unitary. Your input is a completely mixed state in all these n nodes, and a pure state on the control, and somehow you manage to get the result. Okay, so you manage to estimate not the trace, but the normalized trace. So people were thinking, well, this has an advantage. It's got very, very little entanglement. Maybe discord can be. And this is like a year after discord was discovered or invented. And then in 2008, and this is sort of the thing that opened all the new research on discord, people discovered that in this DQC1 algorithm, there is discord at the end. So you start out with something that's separable, and you have discord at the end. And they said maybe this can explain the speed up. Now, when I saw this for the first time, I said, well, that's impossible. How can you do quantum computation without entanglement? And I thought of the following idea. Let's take the quantum gate, this controlled unitary, and split it between 2 laboratories. So Alice has one part, has some of the qubits, and Bob has some of the qubits. Do they need entanglement in order to do this operation? And if the answer is yes, I say, well, look, some of the entanglement that's happening, some of the quantumness that's happening in the process is hidden in this black box, which is a controlled NOT gate. Okay, so what's a controlled NOT gate? Very quickly. So classically, a controlled NOT gate has control and a target. If the control is 0, you do nothing. If the control is 1, you take the target and flip it. Okay, very, very simple operation. In quantum systems, things become much more interesting. One, you can entangle. So a quantum-controlled NOT gate can produce entanglement. Obviously, that's something a classical gate cannot do. The other interesting thing is the target can act as the control. So if I put in the right state into the target, I can flip the control qubit. So if you're thinking about implementing this in two labs, you've got to use one entangled bit. The reason is you're creating 1 bit of entanglement. You've got to use up 1 bit of entanglement. And you're using 2 classical bits, because Alice can manipulate Bob's side and Bob can manipulate Alice's side. We don't want to break causality, so that's what we've got to do. And the question is, what can you do without entanglement? So clearly you cannot do a controlled NOT gate without entanglement. So maybe you can do it on a very restricted set of states. So going sort of back to this DQC1 algorithm, there's only one state that can go into the DQC1 algorithm. Okay, so we know what the input is. So let's look at a very simple example. We say to Alice, look, to Alice and Bob, we say, look, Alice is only going to get the 0 state or the 1 state. Bob is going to get a random state. Can you do this operation? The answer is yes, very simple. Alice makes a measurement on her side. If it's a 0, do nothing. If it's a 1, she calls up Bob and tells him to perform a sigma x, and they do this operation. Another set of states where I can do this is if Bob has an x plus or an x minus state and Alice has an unknown state. Again, Bob performs an operation and tells Alice either to do a sigma z or not do a sigma z. What I'm going to show you now is that if I'm given all 4 of these operations, the gate is impossible to do without entanglement. And I'm going to take a very simple example. Instead of psi, I'm going to have the y plus state. So y plus is the plus eigenstate of sigma y. And it's very nice because in this protocol, I can either take y plus to y minus or not take y plus to y minus. Okay? And here's why this is impossible to do. So you'll note that the 4 states are not orthogonal, so they should be impossible to distinguish deterministically. And Alice and Bob know what they're doing. What do I mean by they know what they're doing? Since they don't have any entanglement, they've just got LOCC. Alice does some operation, she calls up Bob, tells him the result of her operation, he does something, and then they go back and forth. At the end, they can sum up everything they did, work out whatever coins they flipped, anything that was random, they can write it down, and they know what they did. And there's 2 kinds of operation they can do that are relevant, right? There is a set of operations that can cause y plus to become y minus. We'll call that a flip operation. And there is a set of operations that cannot cause y plus to become y minus. We'll call that a no flip. And of all the operations in the world they can do, they have to be in one of these 2 classes. Okay? They know what they're doing, so they know if they did a flip or a no flip, and by doing that, they can discover which state they have. Okay, so example. The first thing you'll note is for each 2 states, for each 2 operations, so there's 4 possible operations, right? Alice makes a flip, Bob makes a flip, Alice makes no flip, Bob makes a flip, etc., etc. For each pair of operations, there's 2 states that are compatible. For example, state A, I know that Bob has to do a flip. He has to take y plus to y minus. But Alice can do anything. She has to take 1 to 1. So taking 1 to 1 doesn't fall into any of these categories. So it could be either or. And state C is the same thing. So for state C, Alice has to take y plus to y minus, and Bob has to do something that, doesn't matter. Taking x minus to x minus, that's compatible with both. Now, again, I tell Alice and Bob, look, I'm going to give you a random state. Can you do this operation? They say, yes, we have this protocol. We're very smart. I give them state A. They run the protocol. Now remember, they have to do a flip. This has to happen because y plus has to go to y minus. They run the protocol, and this is a deterministic protocol. It says if you get a state A, what happens is Alice and Bob will both do a flip operation. They both do a flip operation. They don't know which state they had, but they know it's either A or C. So they can now reverse the operation. Okay? Reversing is very easy because flip and no flip are they're just unitary operations. So you could just do a unitary operation to reverse this. And now they'll do a sigma y. Sigma y pushes state C down to D. So now as far as they're concerned, they either have state A or state D. They now know that, well, they now run this algorithm again. Remember, the algorithm says if I get state A, we do a flip-flip operation, but flip-flip is incompatible with D. So they know with 100% certainty that they had state A. Okay, so now if this was, say, non-deterministic, they could do this millions of times until they get contradiction. Okay, so this protocol allows Alice and Bob to distinguish between non-orthogonal states. And we say, well, if it allows them to distinguish between non-orthogonal states, it's an impossible protocol, so this cannot be done. Okay, and this actually covers almost any quantum state that's going into a controlled NOT gate. So the controlled NOT gate is impossible to implement without entanglement for almost all quantum states. Okay, so quantum discord. Discord is basically a measure of the change in a system before we make a measurement and after we make a measurement, but the measurement is only on one side. In this case, we'll take Alice's side. But we'll usually want to average out, so we don't look at a specific result after a measurement, but we look at the average. So you can think of this as decoherence. System decoheres. The change after decoherence is going to be the discord. But we want to relate this to classical information theory. So let's say we have a classical distribution, and S here is the Shannon entropy. So we've got a classical distribution, Shannon entropy on A and B, and some joint entropy. And we make a measurement. After making a measurement, for each result that we have, there is some corresponding outcome on there's some new information we learn about Bob's side. So Bob's entropy goes down because we know something new about him. There's less information. There's less hidden information on Bob's side. And on average, it's given by this expression. And the difference between the information on Bob's side before I found out something about him, before I made a measurement on Alice's side, and the information on Bob's side after I made the measurement is going to be mutual information. So using Bayes' formula, we can find the more standard quantum expression for mutual information, SA plus SB minus SAB. But if we go to the quantum case, these things are not equivalent. Intuitively, when we say we make a measurement and we find out things, the first thing you ask in quantum mechanics is, what measurement did you make? So clearly, this is measurement dependent. So depending on the measurement, well, this side is measurement dependent, this side is measurement independent, so they're definitely not equal. And this is the basic idea for discord. So we've got three expressions for correlations. The first one is the mutual information. It's taking one type of classical expression for mutual information and just bringing it into the quantum regime. The other one is the classical correlations. That is, taking this other expression for mutual information and bringing it into the quantum regime. But you can read this in the following way. What is the maximum change? So here we're going to optimize over all measurements. What is the maximum amount of information Alice can know about Bob? Okay? By making a measurement on her side. It's very intuitive for classical correlations. And the third one is the quantum discord. Quantum discord is what is the difference between mutual information and the classical, the amount of classical correlations we can get. That's the leftover quantum correlations. So, examples of discord. So one example is taking the state that's either 0, 0, or 1 and plus. And you can see that discord kind of captures the idea of superpositions here, right? And discord here is 0.2, the discord of Alice given a measurement on Bob, but it's 0, the discord of Bob given a measurement on Alice. So we can make the perfect measurement on Alice that is the 0-1 basis, and find all the information about Bob. But the other way is impossible. So the thing we see in this example is discords asymmetric. Another example is the symmetric example of the same thing. And this is, the graph here is how we optimize. So we optimize overall orthogonal measurements. Ideally, you would optimize overall POVMs, but that's just really difficult. And there is a difference. So optimizing over POVMs will sometimes give slightly lower discord. Okay, so discord is not symmetric, and separable states can have non-zero discord. I think the fact that separable states can have quantum correlations is the big idea here. But maybe an even more interesting thing is what are the classical states according to this measure. And this is where this measure really becomes beautiful, because it coincides with a bunch of other ways of thinking about classical states. So a classical state, given a measurement on Ellis's side, so it's not going to be symmetric, is a bunch of pointers that are orthogonal on Ellis's side, pointing to something on Bob's side. You can think of it as a probability distribution on Ellis's side that points to some results on Bob's side. After a von Neumann measurement, the resulting state will be a classical state. So you can think, alternatively, a classical state is any state after a von Neumann measurement. And for any classical state, there exists a von Neumann measurement that doesn't disturb the state. Okay? And it turns out that almost all states are not classical. So the classical states have lower dimension than the set of all states. Now, if we look at classical states, we can define different types of quantum discord. So one is the change in mutual information, which is the standard quantum discord. So the change in mutual information before we made the measurement and after we made the measurement, and again, we optimize, we maximize.
Is that only for the projector-based?
That's only for the, yes, that's right. But you can, so you can take POVMs here, but you have to be careful in how you choose rho prime. So you can there's a method to make rho prime classical after a POVM. Instead of taking the result of the measurement, you can just assign pointers. So it is possible to do this with POVMs. Okay, the second one is a change in entropy. So if you're thinking, why do we do the change in entropy? But you'll see that in the next part of the talk. Then there is the relative entropy. So this comes from entanglement measures, and we've got the relative entropy from the closest classical state. So how far is this from the closest classical state? Turns out that this is completely equivalent to the thermal discord. So it's completely equivalent to saying the minimum entropy, the minimum relative entropy from the closest state after a measurement. So that's I think pretty interesting. And then we've got geometric discord, which is just taking a geometric distance. And again, we can do the same trick and say what is the distance between the closest classical states, and these things are completely equivalent when we optimize. And then there is a last one, which is the change in the measurement when the measurement is in the eigenbasis. So you can think of it as if Alice finds out all the information about her probability distribution or her density matrix, what can she know about Bob? And again, I'll touch on this on the entropic version of this in the next part. What is really cool is all of them vanish simultaneously. So all of them agree on classical states. For all of these, it's the same classical states. It's if and only if, including if we do POVMs. So that's very cool. Except for this one. So with this one, you have to be careful with POVMs. because you can't do this trick that I said of extending the density matrix and assigning probability distributions to the results of the POVMs. Okay, so how does this relate to Maxwell's demons? So Maxwell's demon is a being that tries to cheat and get more work from a system than the second law of thermodynamics allows. The way he does it is he puts a particle in a box, or he gets a box with a particle. The box is thermal, so it's connected to some thermal bath. And he puts a barrier in the middle of the box. He then looks at which side of the box he has the particle. If it's on the left side, he lets the barrier go right and extracts work out of that. If it's on the right side, he lets the barrier go left, extracts work out of that. And he can do this an infinite number of times until the bath is cool, goes to 0 temperature, and he gets all the work that's possible. So that's a perpetual motion machine of the second kind. It should be impossible. And it is impossible because he has to keep on writing down the results of his measurements. When he writes down, when he has to delete them at some point when his memory runs out, he has to pay off work, and the work is exactly the entropy of the system. So for the demon to be efficient, he has to know in advance what the state is. The more he knows about the state, the more efficient he's going to be. If he gets pure states, he's going to do this with maximum efficiency, but that makes sense because he gets a system with 0 entropy. If he gets very mixed states, he's not going to be able to do it. And of course, if he does this once, this trick once, then he's not allowed to do it again because the particle is in a random position. Same thing works for the quantum demon. But we're interested, again, in this bipartite paradigm. So we've got 2 types of demons. We've got the regular demon, he knows everything, he can do everything. And these local goblins. Local goblins can only operate their own little systems, and they get information from the demon. Now, there's 2 different strategies. Strategy 1, they get the information from the demon. One of them extracts work out of his system by he does that by making a measurement and extracting work, takes the result of the measurement, sends it to Bob. Bob looks at the result of the measurement. Now he's got a new density matrix, which is lower entropy. He uses that to get more work out of the system. So by communicating, they can get more work out of the system. You can compare this to the quantum strategy or the non-local strategy where the demon has access to both boxes and just does the optimal work. And there's a difference. So again, we've got Charlie. He sends the information to Alice and Bob. The net work they can do is given by the maximum amount of work they could have done minus the entropy of the measurement on Alice's side minus the entropy of Bob given the result on Alice's side. Okay? But then you've got the quantum demon. He just does the maximum amount of work minus the entropy on both these things. So you can see this is SAB. This is kind of like SASB. So you can see this is related somehow to mutual information. And the difference between what the demon can do versus what these 2 local goblins can do is given by this thermal discord. Okay, so this is where the thermal discord is interesting. But there's another scenario that you can think of. Imagine what happens if Alice only knows locally what she has. So in this case, Alice is completely local. She gets information from the demon only about what she has. She does the measurement. Which measurement should she do? The one that optimizes her own work because she has no idea how she's going to work with Charlie. She still sends information to Charlie because it's still going to help him. So this other type of discord that I mentioned here is going to be the difference between what she can do and what the demon can do. Okay, so there's, again, different types of discord are going to relate to different types of strategies that are allowed by these local goblins versus the optimal strategy of the non-local demon. And again, for classical states, there is no advantage. So if you've got a classical state, Alice does her measurement, she gets the maximum amount of work she can do out of it, sends the information to Bob, he does the maximum amount of work, and the non-local goblin can get exactly the same amount of work from this. Okay, so how does this all relate to distributed quantum gates, or how does discord relate to distributed quantum gates? So again, I'll remind you of this paradigm that we're working in. You've got some unitary operation that is given to Alice and Bob. This unitary operation is impossible to do without entanglement, but you give Alice and Bob a bit of an advantage. You tell them, look, you don't have to do the unitary operation proper, you only have to do the unitary operation on a given set of states. So I'm just giving you 5 states, get the right result. I promise you no superpositions, just these 5 states. And it turns out that it's impossible to implement this on a set of pure states if discord changes. In fact, I'll be a little bit more precise, on a set of discordant pure states if discord changes. So if the states start out with a little bit of discord and I'm changing discord along the way, I can't do it. Now, the reason I'm saying changing discord is if this unitary is just a set of 2 local unitaries, then of course they can do it. But this doesn't change discord. So discord is invariant under local unitaries. Okay, so just a very hand-wavy explanation of why this should be true. So imagine what Bob can do on his side. He can perform an operation. He can make measurements and send information to Alice. And he can receive some information to Alice and act on that information. But remember, if we have discord, we're going to lose information by making the measurement. Now, the overall operation should be unitary, so we don't want to lose information. So these things are not allowed. If he's not allowed to make a measurement, of course he's not allowed to communicate with Alice, because that would be stupid. I mean, he's got nothing to say to her. So he's only allowed to perform an operation. Now remember, we've got an overall unitary, which means that his overall operation has to be equivalent to a unitary. So we've just got this kind of thing, and discord cannot change. Okay, so to sum up, the sort of take-home message from this talk. 1, almost all states are going to be quantum states. Okay, almost all the states in our Hilbert-Schmidt space are going to be quantum. And again, the intuition for this is take a maximally entangled state and add noise to it. It's going to stay quantum until we reach the completely mixed state. The second thing is quantum correlations are an indication that an operation requires quantum resources. So we've got to distinguish between 2 things. Quantum operations require entanglement to be quantum, or at least when you take this LOCC paradigm. They're only quantum if they use up entanglement along the way. But classical quantum states don't need to be entangled. They can be discordant, and it's enough to say, look, you can't do anything with this state the way it is without quantum tools. This is why the state is quantum. And the question is, at least sort of quantum computation, the question is, can this be used to identify the quantum advantage, say, in a quantum computing protocol? So do we need a lot of discord in order to do good quantum computing? And by a lot of discord, we don't need a discord at the beginning. So we don't need to start out with something with discord. That will usually be a bad sign. We want discord somewhere in the middle. We want our gates to produce discord, to change discord along the way. That's it. Thank you.
On the slide where you gave all the definitions of different types of discord, there was the thermal discord, the geometric discord. Yeah, and so it reminded me of the multiplicity of definitions of entanglement measures.
Yes.
In the context of entanglement, there's a set of criteria that any entanglement measure has to satisfy. And the most important one is that it's monotonically non-increasing under LOCC operations. Okay. So I guess I'm wondering what is the criterion that qualifies any given measure as a discord measure?
That's a good question for me. So we just recently wrote a paper, me and Kavan Modi, on a set of criteria. And this is exactly, the criteria you're describing is exactly the reason we put up this set of criteria. So the discord is very different from entanglement. It's different because it's not a resource. So we can change discord using LOCC, right? I'll show the example. Going back. So too many slides. Doesn't matter. I'll just write it down. So the best example of discord, I mean, you can think of it, it's separable, it's very simple, but the best example of discord is 0, 0, 0, 0, plus 1, plus 1, plus. Now, you can clearly see that starting from 0, 0, plus 1, 1, you can create this state just by using LOCC. In fact, you don't even need communication for this. Just by local operations, you can do it. You measure your state. If it's a 1, you do a unit there. So that criteria of invariant under local operations doesn't work. It's going to be invariant or non-increasing under local operations. It's also decreasing. I can decrease discord very easily. I make a measurement. By definition, it decreases discord to 0. But there is this classical correlations. So I have too many slides here. Okay, so there is the classical correlations. So when these guys did their work on classical correlations, they said classical correlations are non-increasing under local operations. This was their criteria. I personally don't think that criteria is absolutely necessary.
So can you say it again?
So they said classical correlations are non-increasing under local operations. You can't, just by doing local operations, increase classical correlations. I mean, that makes...
I would have expected the word discord to appear somewhere in the definition. So
no, it's a correlation measure.
What's that?
That's a correlation measure.
So
you're saying something that has no discord is something...
No, this is just the classical part of the correlation. So the left... So you can think of the total correlations as discord plus the classical part. They didn't think of discord. They were thinking just what is the classical part of the correlations. And they said this one is non-increasing under local operations. You can't
and
by
local operations. You mean LOCC?
No, local. Well, it's a classical correlation. If you're doing communication, you can increase it to infinity.
Okay, so
just by doing local operations, you can't increase classical correlations. And this definition works. So it doesn't, as long as you optimize over all POVs. But for example, if you don't optimize over all POVs, you optimize over projective measurements, you might be able to increase it. And I don't think that. So I think that I can live with quantum correlations becoming classical correlations just by doing local operations. So that I can see where this trade-off is possible. So in this paper that we did on criteria, we had a set of criteria that we called debatable And there are criteria that come from entanglement. So you're saying entanglement is not increasing under LOCC. We don't think that there's an equivalent of Discord. So possibly Discord is not increasing under LOCC if you don't change entropy. That's possibly a definition there.
Because I think it may also be that if you regularize it, then you get it to be, these measures to be monotonic. So if you take many copies and look at your measures and look at how it acts on many copies, then you may go back to being a monotonic function on a class of operations. So, for example, there's measures of classical correlations, which so there's examples of correlation measures which we actually introduced, which were very similar to these thermodynamic approaches. And when you look at the single copy thing, then you see that it's not a monotonic function. But when you regularize it, then you find that it suddenly becomes monotonic. So these things which aren't measures of classical correlations, for example, become measures of
but in your case, it's a measure of classical correlations. So it's,
well, I think even in the well, because what it is, it's the difference of two quantities that kind of how well you can achieve a task under LOCC, like thermodynamic task, versus how well you can achieve it under just local operations.
Yeah, so it's basically the thermal discord. It's not so.
Right,
But
and
you
that
can do this
monotonizes
trick.
that becomes monotonic when you look at many copies. If you do the same thing with comparing an LOCC operation versus a global operation, that also might become monotonic if you regularize it. We don't know. I don't think we know the answer to that.
So I think this example pretty much. So because you can take a state that has, I mean, in your case, discord is, it's more or less the same. I mean, the classical states are the classical states. I think if you take many copies of classically correlated states, maximal classically correlated states, you can definitely make them more quantum just by doing local operations. Or does this go to zero if you take many copies? So this example of 0, 0